All right, guys. So last time, one of the things that we did was we talked about the principle of superposition as a new technique for analyzing circuits. Remember, one very important thing regarding the nature of this new technique is that you can only solve circuits that contain two or more independent sources. Whether they be voltage sources or current sources, it doesn't matter, but there must be at least two of them for this technique to apply. Now, we did go through the theory. However, the theory itself nearly as useful as when paired with an example. So that's the purpose of today's video. We want to go through an example in which we apply the principle of superposition in order to solve a practical circuit. Now, the circuit that I have in mind looks like the following. An independent, let's go to the black pen here. There is an independent voltage source here with this particular polarity that provides us with 110 volts. This in turn is hooked up to a resistor here, a resistor there. There's one down this middle branch, one more resistor here, and then at least this bottom portion of the circuit is complete. And the second source is at the very top port of the circuit, like this. It is not a voltage source, it is a current source, providing us with 4 amps worth of current that way. Now, this is a 5 ohm resistor. We have a 2 ohm resistor there, a 12 ohm resistor, and lastly, a 10 ohm resistor. And the physical parameter of interest, and this is really key, is the voltage across this 10 ohm resistor, and I really want to highlight with this polarity, right? So it's going to be important later on as we go through the problem that the polarity of the voltage that we're taking a look at, that must be respected. Now, the basic idea behind this problem is that when both the voltage source and the current source are acting on that circuit, both of them acting together create that voltage V across the 10 ohm resistor. You can find the same voltage by activating one source at a time and turning off all the rest, finding the voltage across that 10 ohm resistor, and then algebraically adding all of those voltages together in order to create the full voltage. So here, since we have two sources, we actually have to split this into two separate problems. So let's begin with the first portion of the problem. I'll just say that this is part 1. And in this part, I'm going to turn off the 4 amp source while keeping the 110 volt source active. Now, one thing that's really important here, and this is something that was covered in the last video, is when you turn off sources, right, you must replace them with their equivalent circuits. Whenever you happen to turn off a current source, that current source is actually replaced with an open circuit, right? So it's really important to remember here that the 4 amp source, current source, is now being replaced by an open circuit. So let's take a look at what that circuit would look like. The 110 volt source is still there, is still hooked up to a set of 4 resistors, like so. This is a 5 ohm resistor, a 2 ohm resistor, a 12 ohm resistor, and lastly a 10 ohm resistor. Now, the current source used to be up here. So notice that I'm actually kind of drawing in with a dashed line the current source. except it has been turned off. This is now providing us with 0 amps, right? Notice that I have replaced that entire thing with an open circuit. And lastly, before we can actually do anything, is we need to figure out where the voltage is that we're actually trying to solve for when we turn off the turn off the current source. Now again, remember that the voltage that we're looking for is the voltage across the 10 ohm resistor with that particular polarity. Now I don't want to give it the same name V, so I'm going to actually give it a separate name. I'll do this in green. It has this particular polarity, and I'm going to call this V prime. Now the prime here is not denoting derivatives. Sometimes in calculus you actually use a prime to denote a first derivative. Here it's just a different variable name, right? Now if you take a look at the resulting circuit, it should be very, very clear that these two resistors happen to be in series with one another. I can add them in series, and then I can actually add them in parallel with that one. And it's going to give me one equivalent resistor across that section, and the voltage across that, once I actually collapse them into one single resistor, should be the same voltage V prime that I'm actually looking for. So here, I can add the 2 ohm and 12 ohm resistor in series and then add it in parallel with a 10 ohm. So here, the equivalent resistor is the 2 ohm plus 12 ohm, that's 14 ohms, so it is 14 ohms added in parallel with 10 ohms. So that's 14 times 10 ohms divided by 14 plus 10 ohms. Right, so this is the equivalent resistance of all of those resistors added together. I have a calculator here. I can't calculate that in my head. So it is 14 times 10 divided by 28, actually 24, I'm sorry. So 14 times 10 divided by 24. And that gives us a value of 5.83 repeating ohms. So I'm just going to carry it out to that digit like this. So this top circuit I can rewrite as an equivalent circuit in the following manner. I have my 110 volt source, a 5 ohm resistor there, my equivalent resistor there, and the voltage that I'm looking for is this one. And this equivalent resistor value has a value of 5.83 ohms. Whoops. Let's rewrite that like this. So this is the equivalent circuit. Now, notice that this circuit right here, very common circuit, it's a voltage divider, right? So we can even say, hooray. This is a pure voltage divider, which means we can actually use voltage division to solve for the voltage V prime. So here, by voltage division, we do get that V prime is the R equivalent, 5.83 ohms, divided by the series sum of the 5 ohm resistor added in series with the R equivalent resistor. So this is 5 ohms plus 5.83 ohms times the voltage of the source. That happens to be 110 volts, which means I can go back to my handy dandy calculator. So 5.83 times 110 divided by, this is 10.83. And this gives us a total voltage of 59.2 volts. Now, there are more digits that go along to this, but I'm just getting at least the first few. So this is important enough to box. So here, right below that, I'm going to write that V prime is 59.2 volts, and I'll close the box. That's something that we're going to keep in our back pocket. Now that solves for us the first part of the problem. Let's move on to the second part of the problem. So here, this is for now part 2. And in this instance, we're actually going to keep the 4 amp source active, and we're going to turn off the 110 volt source. So here, we're going to turn off the 110 volt source while keeping the 4 amp source active. Now, again, remember that unlike the current sources, when you turn them off, or you replace them with open circuits, when you turn off voltage sources, you don't replace them with open circuits, you actually replace them with short circuits. You replace them with wires. So here, we're going to replace the 110 volt source with a short circuit. In other words, just another wire. So let's go ahead and redraw the entire circuit diagram with this done. So I've got my 4 amp source that's left active up here. Down here we have 1 resistor there, 1 resistor there, 1 there, and lastly there's 1 last resistor here. This is a 5 ohm resistor, a 2 ohm, a 10 ohm resistor, and then lastly a 12 ohm resistor. Now, between this node and that node, this one and this one, we used to have a 110 volt source here. However, we have turned it off. That's one of the reasons why we're replacing it with a short circuit. So notice that I just have a straight wire there. On top of that, the voltage of interest, right, is still the voltage across the 10 ohm resistor with the original polarity respected. So we have the 10 ohm resistor there. That means that the voltage of interest here, I'm going to have to give it some other name. The first voltage I called V prime, I'll just call this V double prime. Again, this does not denote differentiation. It is not the second derivative of V with respect to anything. It's just another variable name. And the voltage polarity that I must respect looks like this. Right. So now I can use any technique of circuit analysis that I want in order to solve for this. Except I'm going to do something clever, because you can use node voltage method, mesh current method, really any method that you want. However, I'm actually going to go back to a physical argument, right? One of the things that I want to be able to show is that despite the fact that it really doesn't look it, 5 ohm resistor and the 10 ohm resistor are actually in parallel with one another. So one of the things that I'm going to do here is the 5 ohm resistor here, what I'm going to do is I'm actually going to, whoops, looks like I erased it rather than moved it. So let me add that back in. So this is what we had. So this 5 ohm resistor, one of the things that I'm going to do is I'm just going to bend it upward like this, keeping everything else in the circuit absolutely the same thing. Notice that the voltages and currents in bending that resistor upward have not changed whatsoever. All the voltages and currents are staying the same, even through the act of bending. Now, this 10 ohm resistor, one of the things that I'm going to do is, instead of bending it, what I'm going to do is I'm going to take this little point and I'm going to start sliding it, right? So here, for example, I might slide it from there to there like this, right? Now, that voltage, V double prime, is going to stay the same even if I slide that end of the resistor over, right? And I can actually keep on sliding this over and over and over all the way up until the end of that resistor ends up at that node, right? So the equivalent circuit that we're going to be working with consists of our current source. We have, our 4 amp current source. We have one resistor up here that's been bent upwards. This is the 5 ohm resistor. The other one I've bent downwards, kind of like this, and slid it all the way from where it used to be. This is the 10 ohm resistor. We have our 2 ohm resistor there, our 12 ohm resistor here. And then the rest of our circuit is complete. And the voltage that we're looking for is the voltage between that node and that node, V double prime across that. Now, with this sliding action, it should be very clear that the 5 ohm and the 10 ohm resistor are actually in parallel with respect to one another, right? Now, one of the things that you should also see is I can add these two in parallel and replace them with one equivalent resistance. So I'll define Req as the parallel sum of the 5 ohm and 10 ohm resistor. So this is 5 ohms times 10 ohms divided by 5 ohms plus 10 ohms. I have to use a calculator for that as well. So here, 5 times 10 divided by 15. This is 3.33 equivalent, and again, it's repeating. Right? So the equivalent circuit that we have now looks like this. We have a 4 amp source, our equivalent resistor there, 2 ohms, our equivalent, this is 3.33 amps, and then down here, and I'm just going to move this 12 ohm resistor down slightly. And the voltage that we're looking for is V double prime. It is that voltage with that particular polarity. Now, one really important thing here is notice that now what we actually have is not a voltage divider, we actually have a current divider, right? So there is going to be a current that we can actually find using current division that's actually traveling down this top branch, right? So this current right here is traveling through that branch right there, right? And I'll call this I double prime. If I can find that, I can multiply by the resistance of 3.33 ohms. I get the voltage V prime. However, we have to respect the passive sign convention. Notice that the current, using current division, as this 4 amp current goes in through there, it has to go in that direction. However, that current is going in the direction of the voltage rise, not the voltage drop. So we need to add in a minus sign by hand. So by current division, we can find that I double prime is 1 over the 3.33 plus 2 ohm of that branch divided by the equivalent resistance of this branch plus that branch put together. So that's 1 over 5.33 ohms plus 1 over the 12 ohms times the current entering into that. That's 4 amps, like this. And if you were to crank through all the math, one of the things that you would find is that this actually is 2.769 amps. Right. Lastly, V double prime is that resistance, 3.33 ohms times 2.769 amps. I have to add in a minus sign by hand. This is actually negative 9.231 volts. And we're almost done. Let me box this. We can now say that by superposition, the original voltage, V, is the algebraic sum of V prime plus V double prime. We have 59.2 volts. We just now find this to be negative 9.2 volts. This adds up nicely to 50 volts. And this is the voltage across the 10 ohm resistor with both the 4 amp and the 110 volt source activated at the same time. You can verify that if you want, but you get the idea. Thank you for watching.